Okay, so here, let me just grab it. So yeah, there's no F. There's just M. So M is 1 kilogram. This I don't think it matters, but you know what? We'll roll with it. I think it cancels out, but it's okay. So if M is 1 kilogram, this block has a mass of 1 kilogram, and this block has a mass of 2 kilograms. Right. Okay, so this is a classic Atwood machine. So there's a couple of different ways to analyze this. I'm going to show you both of them because that's probably the proper way to teach this. So I'm going to do this twice. The first time, I'm going to do it the long way, and then I'll show you the shortcut the second time. The long way is the more consistent way of doing these problems, where like if you get stuck or if you have an extremely complicated one where you can't use the shortcut sort of intuitively, if you do it the long way, you're basically guaranteed to get it fine. So we'll do it the long way first. And the way the long way works is you just have to free body diagram both of the objects. So there's two objects that we're concerned with that are moving in this problem, right? There's the block on the left and the block on the right. I'll call them A and B, right? So we want to figure out, which direction and how fast is A going to move. We want to figure out which direction and how fast is B going to move. So when I say how fast are they going to move in air quotes, I'm talking about their accelerations. I'm curious what their accelerations are because we don't know. Whenever you have that set up, you're like, okay, I want to know how these things move, and you know something about the situation about how they're arranged. Typically, what you're going to go into is a F equals ma problem, right? So we're like, all right, forces. What are the forces acting on block A? So for block A, here's the thing about forces. So as far as we're concerned, gravity is going to be a concern, right? Things get pulled by the force of gravity downwards. So that arrow is going to show up on any of your problems that have the sort of possibility of vertical motion. If something is being pulled upwards or downwards, gravity is going to contribute to that, right? So there's definitely a force of gravity on A. And the strength or the magnitude of the force of gravity is always mg, right? So that's the thing. It's always m times g. G is 9.8 or 10. Depending on who you ask. AP test is totally valid to use 10 as a sort of, rounding thing, right? 9.8 is also rounded, but it's less rounded than 10 is, but it's mg. So for us, the force of gravity on block A is its mass, which is 1 kilogram, multiplied by 9.8 or 10, but mg. I'll just write mg. Okay, that's the force downwards. Now, outside of gravity, the only force that's ever going to affect an object in a physics 1 problem is going to be caused by direct contact with another object, right? So if you want to move something in the real world, normal force is an example of that, right? If something's sitting on the table or on the floor is in contact with it, so it can push on it. So there's a force, right? But yeah, just in general, if you want to push on something, if I want to move my water bottle, right, I can't summon it using the force, right? Like the Jedi mind force, right? I have to actually reach over, touch it, grab it, and apply a regular, good old-fashioned normal force to it in order to hold it, right? So when you're thinking about objects in your physics problems, you want to think, okay, well, what is my object actually touching, right? What is block A actually touching? Is it touching the ground? No, right? It's hanging above the ground, right? It's way up here dangling from the ceiling, right? So there's no normal force, but it is touching the string. So the string is pulling on the block in the upwards direction. So there is the force of a string is generally called a tension, right? So I'll label this T. So for block A, there's gravity, which is, there is no normal force here. But there's tension and gravity, right? There's tension up and gravity down. And sure, you can ask a question, is F tension equal to F normal? Yeah, sometimes not, right? Under what circumstances would that be true? That would be a reasonable question to ask. What would it imply if the rope pulling up is just as strong as gravity pulling down? it might be helpful to think about that the other way, right? What happens if the rope pulling up is stronger than gravity pulling down? Or maybe what happens if the rope pulling up is weaker than gravity pulling down? What happens in all these different situations? Just roll that around in your brain a little bit. It changes how it moves, right? If you pull up harder than you pull down, it's like a tug of war. The rope is in a tug of war fight with gravity. If the rope is stronger, the block will move up. If gravity is stronger, the block will move down. If they're exactly the same strength, the block will not move anywhere, right? So I'll ask you again, what do you think is true? Is T bigger? Is tension bigger? Is gravity bigger? Or are they the same in this particular situation? What do you think? Okay, are they equal? That would imply that it's not moving, right? So tug of war, if T up, mg down, if they're equal, it's not moving. Does block A look like it's going to move if you actually set this up in real life? If you took a piece of rope, tied a heavy block to one end and a light block to the other end, and then threw it over the top of some sort of pulley, right? And then you let go, would it just stay put? Okay, what would happen? Right. So we expect, even before we've done any math, right, we expect block A to go up and block B to go down. Right? So we don't have to do any math. We already know T should be bigger than mg. And we can look at the other guy and run a similar analysis, right? So let's do that. So if we look at block B, right, block B is a fat boy, and he's got a force of gravity downwards, which has, this time the magnitude is 2m times g, and then he also has the same tension force up. And now it's worth noting that for a single piece of rope, the tension should be the same at every point along the rope. So this rope is one big continuous rope. He should have the same tension on the left as on the right. So I'm going to reuse the variable t here because it's the same tension. Now we can write down some equations. So relevant equation here is F equals ma, right? So the total, what color should this deserve to be? So the sum, what's wrong with my sigmas today? The sum of all the forces is equal to the mass of an object multiplied by the acceleration of the object. What we need to do is we have two objects. We need to write this equation down for both of the objects. So for the block A, the sum of the forces, we need to add the two forces together. Now, the way you add forces is you literally just add them together. But the thing to keep in mind here is that forces are vectors, and vectors are going to have directionality to them. They can have positive and negative signs, which indicate their direction. If you're doing a one-dimensional problem. Two-dimensional, you got to do components and all that stuff, but forget all that. We're not there yet. So for this case, the mg, the force of gravity, is pulling downwards, and traditionally we like to define the down direction to be negative. That's just normal. So for block A, the total of the forces is the tension force, which is positive because it's up, plus the gravity force, which is negative mg. So that's all of the forces acting on A added together. That needs to equal his mass times his acceleration. Now there's something to note here. This is the acceleration of block A, and it can be different from the acceleration of block B. So I'm gonna denote that with a subscript. For block B, same thing. You got tension up. So we're adding the forces together to fill out this equation. He has tension up, and then he has negative 2mg downwards, and that needs to equal his mass, which is 2m, times his acceleration, which is, I'll call it the acceleration of block B. Okay, now the reason I bring this up is that the A's are different, is because they are different. You actually already called it out, because block A is going to move up and block B is going to move down, right? That means that the actual numbers that represent their acceleration are going to be different numbers. One of them is going to be a positive number for up, and the other one's going to be a negative number for down. Now, the thing about that, though, is that even though it's technically a different number because one's up and one's down, right? It's the same magnitude of number, right? If one of them's positive 2, the other would be negative 2. The reason we know that is because if block A moves up 1 meter, block B would have to fall 1 meter, right? Their motions are exactly tied together in terms of the magnitude. So we can use one variable to represent their accelerations as long as we denote the proper direction with sign, with SIGN, right, with positive or negative sign. So what I'm going to do is the acceleration of A was upwards, so I'm going to put a positive A here. And the acceleration of B was negative, so I'm going to put a negative A here. Okay. And then we have this wonderful system of equations here. Actually, let me... Yeah, we've got this system of equations here. So what I'm going to do is I'm just going to move this. Okay. We can solve this system of equations, right? Because we have we know M, we know G. M is 1, and G is 10. So yeah, the acceleration of due to gravity, we're going to use 10 as a. It's like rounding pi to 3, right? It's like it's kind of close enough that it's okay for eyeballing things. So the tension is just T. We don't know what the tension is. Plus, it'll be negative. M is just 1, so negative 1 times 10 is negative 10. Is equal to 1 times A is just A. And then for here, it's T plus negative 2 times 1 times 10 is negative 20 is equal to 2 times M is 2 times 1 with a negative sign and an A. So it's a system of equations in T and A, and then you can solve the system of equations. That's fairly normal stuff. So what can I do? So I'll add 10 to the other side. T is equal to A plus 10. And then I can replace T in this equation with A plus 10. So A plus 10 minus 20 is equal to negative 2A. Add the A to the other side, negative 3, or what? Subtract the A to the other side. Negative 3A is equal to 10 minus 20 is negative 10. And then A is equal to 10 thirds, right? Or 3.3-ish, right? So the acceleration that these blocks, block B is going to go down, A is going to go up. How fast they're going to do that is 3.3 meters per second squared. All right, cool. So that's the long way. Let me recap real quick. Right, the long way was think about every individual object. You could plug back in and solve for tension. So it's really easy, right? You just right here, right? Plug in A equals 3.3 right here. 3.3 plus 10 is 13.3. Yeah. Anyways, so yeah, to recap the long method for solving these pulley problems, right? When you have a rope over the top of a pulley, the method is going to be to identify all of the moving objects in your problem, to draw them separately, label and arrow all of the forces on those objects, and then write out the sum of the forces equals MA for each of them, and then solve the system. That's what we did, right? So we drew the pictures, we drew the arrows, we added the forces together and set it equal to mass times acceleration, added the forces together, set it equal to mass times acceleration, being very careful about what is positive and what is negative, what is up and what is down, right? Anything that is down gets a negative sign. Anything that is up gets a positive sign. Okay, and then after we do that, we just plug in all the numbers, and we had a system of equations that we could solve using regular good old-fashioned Algebra 1 techniques, right? Okay, that's the long way. Or I guess clip it and ship it, right? So I'm just going to back up, and let's do it the short way. So the short way is left what is positive? Or like when they were solving through everything. Okay, they might have been doing the shortcut method too. Oh yeah, I got a positive A. My A was positive 3.3 for my final answer. Check the VUD. No, I'm kidding. But like, I got a positive 3.3. Yeah. So yeah, when you do it this way and you put the negative signs on the variables like I did, your answer should basically always come out positive if you did it right. Actually, maybe that's not true. For an unknown force, if you didn't know the direction going into it, it should work out. But yeah. Okay, they could have also been doing the shortcut. Let me show you the shortcut. So the shortcut is sort of based on this idea of thinking about pulleys as redirecting force. So that's really the job of a pulley. A pulley's job is to redirect force. right? So you pull on one end of the rope. Normally, if you pull down on, now let me just draw a rope. So normally if you have a rope and you have a person, right, and he grabs the rope and he pulls down, right, what happens is the top part of the rope will also pull an object down, right? It's typical normal stuff. So the person pulls downwards, the object gets pulled downwards. No change in direction, right? But because of this pulley, right, the direction of the force is now changed, where if you have a block on the other end and a person on this end, right, if this person grabs the rope and pulls down, he pulls the block up. Magic, right? Not really that mind-blowing, but let's just putting this in context, right? So the job of a pulley is to change the direction of a force. What does that mean about this particular problem? So for this particular problem, almost all of these force problems come down to just this idea of a tug of war, right? Where you're pulling in multiple directions and you want to know which way it ends up moving. You can essentially simplify this problem to thinking about it as block M here being attached to block 2M and a tug of war between the two forces of gravity. So there's the rope tied in between them, right? And then there's the force of gravity on A, and then over here is the force of gravity on B. And that's the tug of war, right? Force of gravity on A is trying to pull it down this way. Force of gravity on B is trying to pull it down this way. And if you just sort of grab the rope from both ends and straighten it out like this, right? You get the picture that I just drew, right? So instead of bending hanging the thing over the pulley, you just straighten it out, and you would get this diagram. Okay. Now what ends up happening, right, is that you know how at the very beginning of this problem I said, okay, you have to draw every object and then draw the forces on the object. Well, as it turns out, the definition of the word object is kind of loose in physics. Maybe I should have said system or something like that. Basically, an object is really made up of like atoms, right? And like there's more than one atom in a box, right? If you have a box, there's a lot of atoms in that box. So why do all of those atoms together get to be called one object just because they're bounded together or something, right? Well, the rope technically like bonds these two things together, right? So there's no reason why we can't think about this with the rope in the middle. If we don't care about the tension and all we care about is the motion of the objects, we can treat this problem, the picture that I've just drawn here, as if you just sort of cover these things with a black plastic trash bag, right? It's exactly equivalent to this problem, where you just have a single object that has a mass of 3m in the middle of two forces. One going one way is the force of gravity on, A, and the force in the other direction is the force of gravity on B. So it would look like this, right? Okay, so this is the shortcut. It relies on you making this thought process where you're like, okay, these two objects hanging over the pulley is redirected the force. If I unredirect the force and just draw it in a straight line, this is what it would look like. And you're like, okay, M and 2M are attached together. They're basically just one object with a rope in the middle. But yeah, you can treat that as one object. And you just kind of glue them together and you think about it as a 3M in the middle. And then now you have one equation, right? You don't have two equations, two unknowns, right? Like we had last time with the system of equations. This time, we just have one object that has a mass of 3. So we can F equals ma for this guy. So the force of gravity on A is the mass of A times g, which was 10, right? And the force of gravity on B was the mass of B, which was 2, times 10, so 20, right? So we have 10 in one direction, 20 in the other direction, and an object of mass 3m in the middle. So F equals ma. We have a positive 20 force and a negative 10 force, because when we think positive and negative, the right is the positive direction and the left is the negative direction, right? So positive 20, negative 10, those are the total forces, is equal to the mass, which is 3 times A, and you can solve for A here. So 20 minus 10 is 10 is equal to 3A, and A is equal to 30.3. It's the same number, right? So a lot easier on the algebra because you don't have to solve a system. Just sort of spits the answer out. Now, if you do care about the tension, you have to break it apart. You have to go back and do it the long way. But if all you care about is acceleration, you can do the shortcut. Yeah. Since acceleration, yeah. Exactly. Yeah, it does. So that's why the phrasing of the question is kind of important. If they just ask you for the magnitude of the acceleration, you would just give the positive number. But if I was writing down the acceleration of b, I would say it's negative 3.3 meters per second squared. Personally, right? I would write this down if I was specifically asked for the acceleration of b. But yeah, on like a free response question on the AP test or something, they probably wouldn't mark you off if you just put positive 3.3, mostly because they don't know how you defined positive and negative. You could have been a weirdo and defined down to be positive and up to be negative for all they know, and you would still be technically correct when you wrote a is positive 3.3, right? So, but in fact, there are some times where you just get lazy, right? You know that your answer is going to be down, and you just define down to be positive for the sake of like having to deal with less negative signs in your problem. So there are times when people will just find it convenient to define down to be negative or down to be positive as an exception to the rule. For me personally, when I'm teaching, I always make down negative just so that I'm consistent. But I am guilty of shortcutting if I if I feel like it.